What about electroactive species adsorption? Well, once we've got species adsorbed on the electrode surface, we can do some electrochemistry on those species, and that's actually become more and more popular recently for a reason I'll talk about in a minute. If we have a molecule O that undergoes an electron transfer to R, again, because it's not a diffusional problem anymore, the electrochemistry will be different. Now, for a reversible system, in other words, a system in which the amount adsorbed of O and R essentially follows the Nernst equation as a function of potential, we get curves that look like this. And these curves are not dependent on the particular geometry of the material, because we're not talking about materials diffusing to that electrode, so it doesn't really matter what the geometry of the surface is. Unlike in a diffusion calculation where it does, you get waves that look symmetrical. I'm not drawing them very well, but let's see if I can draw a little bit better. The idea would be that you'd have curves like this, where you'd have a peak current cathodic, peak current anodic. The peaks are lined up directly over the top of each other, and after we get past the peak, we drop back to zero again. Why do they have this shape? Why don't they have the asymmetric shape of the CV? Well, we don't have any diffusion going on, so whatever's on the surface can accept an electron directly from the metal. It doesn't have to diffuse in or away, so there's no reason to not get complete oxidation of all the material on the electrode surface. And so that's what you're seeing by this curve, is a initial exponential increase in the reaction, but as some of those materials become oxidized or reduced, there's less of those available, so the current then drops until you get to the final point. And it doesn't all occur at one particular potential, because there's always a Boltzmann distribution of the process that would give the width of this peak. And so the peak current is equal to the n squared f squared over 4RT times the scan rate A and this term gamma 0 star. First of all, let's see that the peak current is directly proportional to the area and the sweep rate. The faster we sweep, the higher these peaks are going to be. And but otherwise it's very similar to what we've seen before. Gamma 0 star is just a term that includes the adsorption of the oxidized species with time plus the reduced species with time. We can also define this amount here as our half-peak potential, so-called delta EP 1/2, and that turns out to be .53 RT over NF, or about 90.6 millivolts per N at 25 degrees C. So we increase the number of electrons, the sharper that peak becomes, just like it did in the CV case for diffusion-based processes. And as we increase the temperature, the width of that peak expands as well, suggesting again a Boltzmann type distribution of the molecules. Now this suggests that we've either got only electroactive species adsorbed on the molecule or on the electrode, or that molecules can't diffuse to the surface and undergo an electron transfer process. So for example, you might adsorb some molecules on the surface, transfer it to a solution which there's no adsorption possible, there's no O and R present in that solution, and only the adsorbed molecules can undergo this reaction. Now, as we go to a non-reversible case, I'm not going to really spend a lot of time on that, but what will happen is, just like in the diffusional case, the reaction energy, there's an overpotential now, and so the peaks will shift, more negative for the reduction process and the more positive for the oxidation potential. So instead of symmetric peaks, you'll see an asymmetric peak separation. And you might be confused if you look at this as being a diffusional-based process, but what will be different from a diffusion and absorption-based process by this, what would be a quasi-reversible case, the peak current would basically still be almost the same. There would be a slight difference from the reversible, but probably within 20% of what you see here. But notice that the current drops to 0 in this quasi-reversible adsorbed case, which would not be the case for diffusional-based process. You'd always see for diffusion a curve that would be more like that, or you'd see a curve above 0. So that's one way to tell the difference between absorption and diffusion, is look for that going down to 0. All right. Now, we can sort of force things to be this way of only a molecule being absorbed or reduced. Often what happens, though, is you're doing an experiment where you're looking at material that is diffusional. You want to look at the diffusion-based electrochemistry of the situation, but the material also adsorbs, has a strong enough energy of adsorption that will absorb to the electrode, as well as, so you get electron transfer not only for the adsorbed molecules, but for the molecules that are diffusing to the electrode surface. So if you have both the dissolved and adsorbed molecules or ions are electroactive, then things get a little bit hairy. Let's take a couple of cases. If we have the product of the reaction strongly adsorbed, what will we see? Well, for the diffusion process, we'd see almost the same wave as we'd see for the diffusion if it was not, there was no adsorption going on. So you'd see diffusion alone, you'd see the normal cyclic voltammogram. And again, we're assuming a planar diffusion, a planar electrode here, and semi-infinite linear diffusion. For other geometries, it would have a slightly different shape. But if we have the product strongly adsorbed, what we see is a pre-peak, perhaps something like that, and a slight change in the shape of the wave. But this pre-peak occurring just before the diffusion peak. And so that would correspond to O in the solution undergoing electron transfer. Again, this is reversible in both cases. And we're only talking about the product being undergoing, darn it, the product undergoing adsorption here, not the reactant. The reactant is adsorbed only to a slight extent. So why is that? Why is this happening? Why do we see a pre-peak? Well, because things are adsorbing, that must mean that when you adsorb, you're lowering the free energy of that molecule. Otherwise, it wouldn't adsorb. So by adsorbing that molecule, you're making it easier to reduce in that system by making the free energy of the molecule less. If it wasn't a pre-peak, that would mean that being adsorbed would make it more difficult to reduce, and there would be no reason why that molecule would be adsorbed in that particular case. Okay, so once we have that particular process happen. On the other hand, if the reactant is absorbed, you get peaks that look, like this with the CV, and then with the reactant absorbed, post peaks, like so. And again, same idea. By absorbing that reactant, you make it easier to oxidize, and so those peaks occur there rather than somewhere else. Okay. Now, one thing about adsorption like this, these are strongly adsorbed molecules. In other words, there's a high energy of adsorption for these particular things. One thing you'll notice is, particularly with adsorbed molecules, it's kind of one way to tell if things are getting adsorbed is to adjust the potential at which you start the reaction. For example, if I did the start of the reaction at a negative potential, I might see a different adsorption process in that particular case. Because what's happening is that if we start our electrode at a different potential, we're not letting the material adsorb at the potential of the other one. So there's a different free energy for the adsorption of these molecules, particularly for the product particular case. Things are adsorbed that way. So that's one way to tell things are possible. What about if there's not such a high energy of the adsorption? Well, what happens if the energy changes for this particular process, those peaks are going to shift more negative. As the reaction becomes stronger, the adsorption free energy becomes stronger, those peaks shift more negative for the product being adsorbed, shifts more positive for the product to be adsorbed, more negative for the reactant to be adsorbed, and that's for higher energies. But as the energies become less for adsorption, those peaks start to mingle with the diffusion waves, and that's when things get a little messy, because then we have a hard time sometimes telling whether or not adsorption is actually occurring, because the peaks are not distinct looking in those particular cases. As we get a weak adsorption, for example, a weak reactant adsorption, we get initially a wave that might look like that, but with a reactant adsorption, those waves start to mingle in, and we might see a wave that looks almost identical to a CV. May look kind of a little odd, but you may not necessarily notice anything different about it. But the waves would be merged, and it'd be hard to tell just by looking at it that you've got adsorption occurring. So the waves would not look quite right. What you'd notice particularly that the peak current would not be proportional to the v to the 1/2 power, as you'd expect for a diffusional wave, because as you mingle in that adsorption wave, remember the adsorption processes is IP is proportional to the scan rate. So with adsorption, as we increase the scan rate, you're going to get IP is more and more proportional to V for adsorption. So at low scan rates and high scan rates, you're going to get a shift for the peak current being proportional to V to the 1/2 at very low scan rates, and then peak current would be proportional to V at high scan rates as you shift for the dominance of those two. And this is for reactant adsorption. For product being adsorbed, you'd have a similar thing, except the wave would come up a little higher on the forward process rather than the reverse, and so on. Well, it's hard to tell sometimes from the CV. It's a little easier to tell with other methods. One way that people have used to tell if we're getting adsorption on the electrode surface is to use double potential step chronocoulometry. The the idea here is, remember coronal coulometry where we did a potential step and we converted the current to a charge, or we directly measured the charge, and if we plot the charge as a function of the square root of time, we got a straight line in principle. Now this assumes that the reactant is absorbed. Why are we assuming that? Well, the product is absorbed. We can often avoid, we can actually know how much is being absorbed by looking at the charge that would pass for only the absorbed process and subtracting away from the charge that would be passed from the diffusion process. Well, remember our equation for that. The Q is equal to 2NF A d0 to the 1/2 C 2 pi over tau. This is our Cottrellian type boundary conditions for chronocoulometry. That's the diffusional part of that. Then there's going to be a adsorption part of that, NFA gamma, plus then there's going to be a charge from the double layer charge. So in order to know how much is absorbed, what we really want to know is this particular part here, the adsorbed charge. This is the amount of material, that's the charge that would be associated with the adsorbed species. How can we do that? Well, remember this part of the equation should have an intercept of 0, so anything above 0 is this part here. So this is the adsorbed and double layer charge. So if we can find out this particular value, we can do it. Well, what people usually do is they do a reverse step. So they step back and they'll see another set of data like this that they plot for the reverse charge, and then they subtract off on the reverse step the double layer charge, because the double layer charge and the reverse step and the forward step and the reverse step should be equal to each other, and they can subtract that off. And you can actually define a time in this case where you can see people are fond of using thetas in this particular time frame of electrochemistry. And they said, well, let's define theta as this, and that's just the subtracting off the time it takes to do the potential step. And so the theta on the back, or Q on the back process is equal to 2NF A d0 to the 1/2 C pi to the 1/2 theta plus QDL. And so subtracting off the forward and the back gives us, allows us to subtract off the intercept on the back, that gives us the QDL, and then subtracting that again gives us the amount absorbed. All right. Well, let's stop here for our break, and we'll continue in a few minutes.